Good morning, everyone. So what I would like to do today is not to speak about data assimilation, but more on predictability. And I will do that in the context of a reduced order coupled ocean-atmosphere system. And in fact, this presentation is the fruit of a collaboration between different people, Leslie de Cruz, Jonathan de Meyer from my institute, Michael Gill, and also Roman Solé-Pommiers, a student from École des Mines who did a quite amazing job. So let me just introduce briefly the problem. As you know, the atmosphere displays a wide range, variability on a wide range of space and time scales. And here this is just an example. I call that weather variability. Here you have a time series for a temperature at one specific station in Belgium for about 10 years. And these are daily mean temperature. And the purpose of weather forecast is clearly to make forecasts for this, the evolution of these daily values. So we have a quite erratic behavior around this seasonal signal, and weather forecast is essentially trying to make the forecast on a daily basis. And in fact, there is a typical predictability limit of these forecasts from, say, 1 week up to 3 weeks, depending on the accuracy you want to reach. Okay, but there is also variability on much longer time scales, and here this is just one specific index. It's called the North Atlantic Oscillation Index, which is simply the difference of pressure between two different weather stations, between Lisbon and Reykjavik over the North Atlantic. And these are averages over the winter season. And what is interesting to note in this case, this is a quite long time series, as you can see, what is interesting to note is that you have periods where you have quite low values, for example here, and periods during which we have quite high values. So you have a kind of decadal variability for this oscillation. And of course, we know other signals like ENSO, which is associated to the development of El Niño in the tropical Pacific, which is also another very interesting signal, so low frequency variability signal. So, and of course, we would like to exploit this information and try to perform a long-term forecast beyond these 2 or 3 weeks, as I just mentioned. And in fact, it could be it could have, if we are able to perform such forecasts, let's say on seasonal or decadal timescales, this could be quite interesting. In fact, here you have just one example. This is a negative, so this is a pressure field associated to a negative NAO index for one specific winter season. And what you have here is also the corresponding temperature field. And well, these are temperature anomalies. And what you can see is that you have zones where you have quite cold anomalies, and other zones where the weather is, well, the climatology is milder. So, of course, we would like to use this information, but in fact, the problem is that the climate models have a lot of difficulties to reproduce these dynamics. So there are questions there. What is the source of this low frequency variability? Is it could be associated to some teleconnections, for example, with the tropical Pacific, or it could be also associated with the coupling with the other components of the climate system, like the ocean. And in fact, this is the way we went when we started this work. We want to understand the coupling between the ocean and the atmosphere and see if the low frequency variability which is present in the atmosphere is associated to this coupling. Okay? Okay. So this is the strategy. What we'd like to do in the context of this work is to characterize the predictability of the atmosphere at seasonal, internal, and decadal timescales. And the strategy is to develop reduced order coupled ocean atmosphere models and to investigate the predictability of these models. And of course, as you saw yesterday afternoon, you saw that these models can also be used to test some data assimilation schemes. It was presented by Alberto yesterday, and also for ensemble forecast. Just to mention, we have got very, very interesting results recently on ensemble forecast in the context of coupled ocean atmospheric models, but I will not speak about that today. So, what I would like to present you today is to discuss the emergence of low frequency variability in reduced order coupled ocean atmosphere systems, and also to show you the emergence of the long-term predictability. We'll do that in two different models. The first one is the model we call VDDG, associated with the four authors that were at the origin of this model. And it's the ancestor, in fact, of the modular arbitrary ocean order ocean atmosphere model, MAOAM, that was used yesterday by Alberto, and also a new version of the coupled ocean atmosphere model, for which we change, in fact, the boundary conditions in the ocean. Okay, so let me present you now the model. So this is the first version of the model, the VDDG model. And so, in fact, you have a rectangular domain over which we will integrate the quasi-geostrophic equations for both the ocean and the atmosphere. What we impose so you have two layers within the atmosphere. We have one layer for the ocean. We have periodic boundary conditions in the zonal direction in the atmosphere, and you have no flux boundaries, so you have kind of channel flow, no flux boundaries in the meridional direction. For the ocean, you have closed boundaries, so you have no fluxes through these boundaries, and would say it mimics a bit what is happening in these large ocean basins like the Atlantic Ocean Basin or the North Pacific Ocean Basin. This is for the extratropics, okay? So there are two very important physical ingredients that were incorporated in the model. Here you have a vertical slice of the model, okay? So you have the two atmospheric layers here, and you have the ocean layer. And we integrate the vorticity equation in the two layers, and you have also an equation for the temperature at the interface between these two layers. For the ocean, you have also an equation for the stream function. This is a vorticity equation for the stream function, and you have the temperature, which is considered as a passive scalar. One very important ingredient is the energy balance scheme, which is introduced in the system. So you have net shortwave radiations coming from the sun entering into the systems, partly absorbed by the atmosphere and also by the ocean, and then from the ocean it's re-emitted as long-wave radiation toward the atmosphere, and again it's absorbed by the atmosphere. Okay. And we have also heat fluxes between the two subcomponents of the model. And what is really important, in fact, this is the radiative input. So the radiative input is made from a constant value plus something which depends on latitude. So you put the system in a non-equilibrium situation, and then this will induce the dynamics in this system. So this is proportional cosine of latitude, and CO is really an important parameter in our problem, as you will see later. Another very important element is the friction at the interface between the ocean and the atmosphere. This friction will induce the dynamics within the ocean, of course. And one very important parameter in this case is the friction coefficient C, which is given here. And we also call that D or delta, but it doesn't really matter. This is some renormalization of this coefficient. Okay, so the dynamical equations are there. So you have the vorticity equations. I do not want to enter into too much details. You have the two vorticity equations for the atmosphere. You have the temperature for the atmosphere, and you have the vorticity equation for the ocean and for the atmosphere and the temperature for the ocean too here. And G is just the Jacobian. This is the nonlinear term in our problem. Okay, so we have our partial differential equations, and what we would like to do is to reduce our problem. So we, as done by Lawrence and by many others, by Charney, by Saltzman, what we decided to do is to develop all the fields. Here, this is the barotropic stream function. So this is the sum of the two stream functions divided by 2 within the atmosphere. This is theta, this is the baroclinic stream function, which is associated to temperature. Psi O, here is the stream function within the ocean. And here, this is the temperature anomaly within the ocean. And so we developed that in the Fourier series with the Fourier modes that are, of course, respecting the boundary conditions. We choose to use 10 modes for the atmosphere. And we have, of course, since we do not have the same boundary conditions, we use so different modes for the ocean. And these are the 8 modes we are using. And if you do that, you plug that into our partial differential equations, then you project on these different modes, on the different Fourier modes, and then you get a set of ordinary differential equations. And this model is a 36 variable ordinary differential equation that was developed by Leslie, Jonathan de Meyer, Michael, and myself. This is the original version of the model. The second version of the model is, we call this one Mao-Zoam. And in fact, what we did is to open the boundaries in the x direction. So in the zonal direction for the ocean. So we assume here that we have periodic boundary conditions within the ocean too. So you have kind of 2 channel flows superimposed to each other. Okay? And then in this case, we can use the same modes for the ocean and for the atmosphere. And we have, in this case, used a model of 40 variables. And if you want to use these models, you can find both on GitHub. And I, of course, encourage you to use this model. It's quite easy and fast model. Okay, so let's move now to the variability and the predictability into this model. And this is the solutions of the model, of the original model, so the first version of the model with closed Bayesian boundaries for different values of the parameters. And we have represented here the geopotential height difference. So this is similar to the difference of pressure as the NAO index I presented before within the domain. And you see the solution for about 200 years. Below, you have situations with high values of the radiative input and so differential radiative input, and also small values of the friction coefficient D here. And what you can see is that you have quite highly erratic behavior. Of course, this is reminiscent of the chaotic dynamics within this system, as I will show you later. But what is much more interesting is that when you increase the friction, and this is the picture above here, you can see that you have a kind of oscillating behavior as a function of time within the atmosphere. So we have, you can see here, a low frequency variability developing within the atmosphere thanks to the coupling between the ocean and the atmosphere. Now, clearly, if you are at the back, you can imagine that this dynamic is quite similar to this decadal variability I showed you at the very beginning. Okay? So there's some similarities there. Okay, so, and in fact, we can trace the origin of this low frequency variability in the bifurcation diagram of our coupled ocean atmosphere system. So here we fixed the friction coefficient and we look at the norm of the solution as a function of CO, which is the differential radiative input into the system. And if you look at the solution, here you have a stationary solution, then you reach a Hopf bifurcation, and then you get a new solution, which is a periodic solution here. You have a fold, doesn't really matter. What is important here is this solution, and in fact, so you have a periodic solution here, which is stable, and here you have a periodic solution here too, but unstable. And what is important to note is that the period of this periodic orbit is of the order of 20 years. This is very long, okay? And in fact, you can see here the projection of these periodic orbits in a, so this is a three-dimensional projection of the full phase space. CA1 here represents one important mode within the atmosphere, which characterizes, in fact, the zonal flow within the atmosphere. And you have two other very important variables, CO2 here and TO2. CO2 represent double gyre dynamics within the ocean. TO2 essentially represent the gradient of temperature as a function of latitude, okay? And clearly what you see is that this is indeed a coupled mode between the ocean and the atmosphere. And in fact, if you reduce the friction coefficient, this periodic solution disappears completely. So clearly, this is a coupled mode between the two components of the system. Okay? So just to show you the solution. So this is a movie. Okay? So you have what I showed you before, the geopotential height difference here on this picture. You have the evolution of the solution, so the numerical evolution of the solution in the three-dimensional projection of the full phase space. Here you have the solution for the atmosphere, two solutions for the atmosphere. This is the atmospheric temperature, the barotropic stream function. And here you have the same for the ocean temperature, and here ocean barotropic ocean stream function. What is interesting to note is that you have a very highly erratic behavior at some moments, but once the gradient of temperature within the ocean is quite low, the gradient in the meridional direction, then it's quite, the dynamics is quite it's not highly chaotic anymore, and you visit, in fact, these zones there. So you have this kind of low frequency variability appearing into the system, okay? Okay, so if we compute the Lyapunov, so here this is the three-dimensional projections of two attractors. You have one for small friction coefficient in red, A, and you have the green one, which represents the one with the low frequency variability, so with high friction coefficient. And you have the Lyapunov spectra in this case, and it was already shown yesterday by Alberto, but you have positive exponents in both cases and a lot of exponents close to zero. There is only one zero, but there are a lot close to zero, which are associated to the presence of the ocean. But now let's turn to the most interesting part is the predictability properties of this system. In fact, so we consider just the one where we have the low frequency variability, okay, here. And we have three different realizations of the error. So you start from one initial condition on the attractor of the system, you perturb it, and you look at the error growth, okay? And you have three different realizations. Here, the green one, you see, you can have very, very long predictability times. Here, this is about 2,000 or 3,000 days. But look at the two other ones. So you have very, very rapid growth of the error for the two realization. So the red and the green, the red and the blue. But at some point, you have a kind of a re-emergence of predictability. So the error decreases, and of course, you are going in some specific zones of the attractor. But if we wouldn't have any low frequency variability presented to the system, then it would have been saturating at a high value like this. But here you gain. That means that you are not visiting the whole attractor yet. So you have still your two trajectories close to each other, and you are not like with two random solutions on the attractor. Okay, so and it's after about, let's say, a few years. Huh? So you keep a long-term predictability in this case. And if you look at the average of this error growth, this is what you get. So for attractor A, this is the one without any low frequency variability. I don't want to pay too much attention to this one here. Just look at this error evolution and as you can see, this is for a very long time. This is up to 85 years here, okay? And this is the saturation of the error, I would say. This for the first attractor, so the attractor with no low frequency variability. And you have a saturation which is quite rapid for this variable, just for one variable. Okay. And now, if you look at the case where you have the low frequency variability, clearly you see a diffusive behavior of the error for very, very long times, and clearly indicating that we have predictability for long times. Okay?
What is the blue line?
Sorry? Okay, the blue line, so this is the mean square error evolution average over 1,000 realizations for one specific variable. It's for CA1. And so there are two different, well, this is different set of parameters. So you have the green and the blue. The green, this is for a certain depth of the ocean, and the blue, this is for another depth of the ocean, okay? So but this is for the same variable, all the time for the same variable. This is for the attractor A, and this is these two for attractor B, okay? But with different depths of the ocean. And you have this slow increase for very, very long times, indicating that we have still some predictability in our system. So let's now turn to the second model, where with open boundary conditions within the ocean in the zonal direction. And here this is the evolution of two variables of this model. And the green one is the temperature. This is one mode of temperature within the ocean. What is interesting to note is that you have some kind of excursions from time to time. You have excursions close to zero here, okay? But these excursions are quite erratic in time, okay? And it will make a very, very big difference to what I showed you before, as I will show you, okay? This is for a quite high friction coefficient. And here I have to switch to show you the movie, because otherwise I cannot. Okay. So let's look at the evolution of the solution in this case. So this is, of course, we have changed the geometry because this is periodic boundary conditions. Doesn't really matter. But what is interesting to note is that at some point, so you have again the ocean and here the atmosphere. At some point, the atmosphere is frozen and is evolving coherently with the ocean. Okay, and at that time, you have a quite good predictability of the system. But when you leave this situation, then you don't have a good predictability anymore. And so I will just, okay. How do I switch again? This one. Oh yeah, okay, anyway, doesn't matter. So here you have the Lyapunov spectrum for different friction coefficient. Again, you have a chaotic solution, and you have chaotic solutions, and you have a large number of, yes, okay, exponents that are very close to zero. But what is really interesting to look at is the error evolution in time. Here you have 4 different realizations of the error evolution. You have the red one, which is, well, which is in fact close to this situation where you have this coherent evolution between the ocean and the atmosphere. This is close, in fact, to an unstable periodic orbit. And in this case, you keep quite good predictability for very long times. But now look. Oh yeah, sure, I'll do. Okay. Okay, let's. Okay, it's better. Okay. So yeah, for the other ones, what you see is that you have a very fast growth at the very beginning. And this is given in years here, okay? And then you have a saturation of the error. You don't have a re-emergence of predictability as it was shown before for the other model, okay? And I will finish soon. So you can also look at the different realizations. And clearly for this very long predictability situation, you can make predictions up to 5 years here for this case, and in the other case you cannot. Okay, it doesn't matter. But clearly, what we cannot do is to make, at this stage at least, what we cannot do is to make forecast of these excursions. We cannot make forecast of the transitions close to this unstable periodic orbit. We can make very long time predictions when we are close to this unstable periodic orbit, but we cannot make good predictions to these excursions toward this unstable periodic orbit. Okay, and here this is the long-term predictability. So this is an average over 1,000 realizations for different values of the friction coefficient, and clearly you keep long-time predictability when you have large frictions. But as I said before, the transitions from let's say the main core of the attractor toward this unstable periodic orbit cannot be predicted well. But once we are there, then you can predict for very long times. And this is the conclusions, and just want to say just a few things. First, you can see that the low frequency variability is developing in this coupled ocean atmosphere model when you have large friction coefficient. And it's, so in the first version of the model, the attractor is developing around an unstable periodic orbit, okay? And you can have a very long predictability in this case. For the other model, so the low frequency variability is also developing, but is associated with some excursions close to an unstable periodic orbit. And in this case, you can keep long-term predictability when you are close to this unstable periodic orbit, but not when you are out of this, you are far from this unstable periodic orbit. And I'm finishing here, so thank you very much for your attention.
Thank you very much. I think we have time basically if you were just about one question. You choose.
Two questions.
Okay.
Thank you, Stéphane. I would like to ask, for the atmospheric component of your model, do you have like both the Rossby waves and the inertial gravity waves that are present in the...
We don't have inertial gravity waves. These
it's
are
QG.
equations.
So it's derived from QG. It's not.
Yes, this is just QG model. So.
And what's about doing something similar for primitive equation then?
Oh yeah, please go ahead. Be my guest.
No, but I mean.
Yes, it's possible probably, but but of course it's much more. You have much more equations, and then you will have much more.
Because there is the Lorentz model of the Lorentz 80 model.
That's right. It's a really nice
which is
model.
a 9-dimensional model.
Yes.
And that's a very good model.
At the very beginning, I want to use this one, but the point is that there is a slab ocean, and there is no dynamics within the ocean. You have to reintroduce dynamics within the ocean. But this is a very, very nice model. I do agree, because you have clouds, you have precipitation, you have.
Exactly.
That's a really nice model. Yeah.
We can take maybe one more quick question.
So I always thought that the NAO was not a climate mode like El Nino, but it's just a result of what the atmosphere was mainly doing. So the question is, but you seem to say something different. But of course you don't have a storm track in your model, not really, because you don't have the resolution to have that. But so the question is actually. What you see there in the Atlantic configuration, is it mainly ocean modes that you trigger by atmospheric noise? So the eigenmodes of the ocean that you're triggering, because it looks like just barotropic.
There are two elements that are very important, of course. The first one is that the atmosphere is transferring some momentum towards the ocean, inducing the dynamics within the ocean. But the other very important element is the heat transfer between the two systems, between the two subcomponents of the systems. Otherwise, you will never see these dynamics within the atmosphere. So you need both that are, let's say, competing with each other to get this low frequency variability within the atmosphere. Yeah, this is a key ingredient.
So the question is,
sorry.
Is that low frequency variability due to, is that you're triggering an eigenmode of the ocean, or is it really a real coupled mode?
This is a real coupled mode, but maybe we can discuss that later. Real coupled mode. Yeah.
All right, let's thank the speaker once again. We're already a bit over.
We said 2 questions.
Let's thank the speaker once again.